Okie dokie. How are we feeling today? That's good because it is Tell Me Something Good Tuesday. Who has something good to share better than I have El Campesino leftovers for lunch today? Yes. I don't know. I never took it off and I just, yeah.
No, it's on the arm. Not that. It's on the arm of the chair.
Oh, it's right here.
That's cute.
In case I want to return it. You never know.
How long have you had that?
Like 4 years.
For real?
Yeah. Who else something good? What's good? Yes.
I get to start therapy again.
Oh no, I thought you were okay. Oh, I'm sorry. Who else? Something good. Joseph.
My orthopedic doctor, he said that I don't have fracture, I have just a sprain.
Love that. Good news. You and my daughter are on the same recovery track. So, very exciting. Anybody else? Good things going once. Anyone see Northern Lights? Oh, tonight. Tonight at 10:23. It is supermoon, equinox moon, partial lunar eclipse. 10:23. It's just going to be like the very bottom. Of course it will. Of course it will. But probably not. It's hard. You can't like get good pictures of stuff at night. It's just hard. So 10:23 tonight. Make sure you're watching. Don't miss it. Today, we're continuing our journey into chemistry. We're moving on to chapter 4. The tests are in this pile, not graded. I now have all of them. So my goal is, during detention today, is to grade these. Why are you smiling like that?
Me?
Yeah.
Yeah.
I'm not saying whose fault. No, I'm kidding. We all know. So my goal is to have those graded by tomorrow. Tomorrow we will wrap up notes. I'll go over the tests. Thursday is going to be a prep day for lab. So it's going to take a whole day to prep for the lab, which we're starting on Friday. Yes. After school today. I teach 3, 4, 5. I teach periods 3, 4, 5, 6, 7 straight after first and second. First and second period, I was mixing chemicals for the lab, which starts Friday.
But you get first and second period off.
Only today, because first period I had coverage for study hall. I usually have study hall first period, second period plan, but I mix chemicals the whole time.
That's not. I mean, you get like an hour and a half though. You got to start with that.
Yeah, I mix chemicals for an hour and a half straight.
Well, yeah, but in general, like normally it's not that bad.
Also, let's talk about this hate list. We really don't need to have pierogies and potatoes.
That's what I said.
Because pierogies are made of potatoes. It's kind of repetitive.
I don't like the pierogies because of the potatoes.
Sometimes too. It's different.
Okay, all right. All right.
It's my list.
Is everybody here today? Okay. Nobody. Chapter 4. Chapter 4. We have, I like to call this chapter More Reactions, I know, so fancy, / Solution Stoich. So we are now going to move into solution stoichiometry. When I'm dealing with, well, let's just talk about it. What is a solution? What is a solution? It's a sharpener. If I have a solution of something, what's it made of?
Something dissolved in
Water. It's water-based. It's water-based. And water is known as the what?
universal solvent.
Yes.
Okay.
Is known as the universal solvent. Anybody know why water is the universal solvent? Why? Yes. Because water is polar. Water is polar. By the way, what does the solvent dissolve? The solvent dissolves the solute. So if I was looking at Kool-Aid, my solvent would be what? Water. And the solute would be the sugar. So water is polar. What does that mean? Well, here's water. I've got H plus, I've got H plus, and then I've got O2 minus. Also, there'd be a couple lone pairs. There'd be a lone pair here, lone pair here. Water is a polar molecule. What does that mean? That means if I split water in half, do you see how it has two sides? What side is a what side? Positive side, and this side is a negative side. So, if something with a negative charge comes to interact with water, does it have a side of water to interact with? Yeah. Opposites attract. If something with a positive charge comes to interact with water, does it have a side of water to interact with? Yeah. The negative side. That's why water is the universal solvent. Not just because it dissolves everything. This is the actual why. And sometimes you will hear like dissolves like. This is not an answer on an AP test. All right, never say that on the AP chemistry test, but it helps you remember. If something is polar, it's going to dissolve something that's polar. So water's polar, sugar is polar. They dissolve in each other. There's more involved in that. We're going to talk about that later. Water's polar, oil is nonpolar. Those do not dissolve together. That's because they're not the same, what's called intermolecular forces. We'll get into that later, though. We'll get into that later. Okay, have you seen this chart freshman year? So I have a chart. We had solubility on the Y. You may have seen this in chemistry too. And we had temperature on the X. And then there was like a curve. And there was like an A. There was a B. There was a C. If you had me freshman year, I juggled. Remember me juggling? No, I definitely juggled. Because I was talking about what when I was juggling? If I had one ball, I would be at point C. Yes, no, people did them at me. I was at point C. If I had one ball and I have two hands, only one hand was full, what was that called? One ball. Unsaturated. Yeah, now you're remembering it. If I had two balls, two hands, what was I? Saturated. So that's on the line. That is saturated. And in order to get three balls moving, what did I have to do with the balls? Juggle, because I had to put more what in? Energy. More energy in. That was me juggling. So that A would be super saturated. Super saturated. So A is super saturated, B is saturated, and C is unsaturated. Okay, good. That's very, very basic stuff. Let's make a little chart down here. On the left side, let's have things that dissolve easily. So things that dissolve easily. And on the right side, guess what we're going to have? Things that don't dissolve easily. Or you could write hard to dissolve. I don't care. Don't dissolve easily. I'm going to zoom in a little more. I feel like I could. You guys can see this a little bit better. Is that better? Yeah. The thing is, when I zoom in, I get like self-conscious because then you can see my true handwriting. But no, you guys would never judge me.
Yeah. No.
Wow. Okay. Things. Now I do feel judged. Things that dissolve easily. First thing that dissolves easily are ionic solids. Can anybody give me an example of an ionic solid? Salt. Salt is an ionic solid. You'd agree that salt's an ionic compound, yes. Sodium chloride, positive, negative, yes. So anything that's an ionic solid, or you could have potassium chloride, lithium chloride. Anything that's an ionic solid is going to dissolve easily. The other thing that dissolves easily are strong acids. So put a little asterisk here because you have to memorize the strong acids. You've got to know these. There's 6. So we're going to write them down. The first strong acid is sulfuric acid, H2SO4, sulfuric acid. The next strong acid you have to know is iodic acid, HI. I'm writing them in this order for a reason. Iodic, IODIC.
Why isn't it hydro?
Because there's no oxygen. I'm sorry, you're right. This would be hydroiodic acid. Yes, because hydro is no oxygen. Good catch. HBr, hydrobromic acid. Now we're back on track. HNO3 would be nitric acid, HNO3. HCl would be hydrochloric acid. And the last one would be HClO4, which is chloric acid. How can we remember these? Last year, we finally came up with a mnemonic device for this, which is, so I brought no clean clothes. Do you guys see it? Do you see how that will help you remember it? So I brought no clean clothes. So sulfuric acid, I hydroiodic acid, brought hydrobromic, no hydronitric acid, clean hydrochloric acid, clothes, chloric acid. Or come up with your own. I think it's pretty good. So I brought no clean clothes. We wasted way too much time on that last year. And now we just have it. So if you're watching this for some reason, AP Chem 2324, thank you. It's on YouTube, so they could watch it back.
I'll tell Maggie to
Yeah.
give a look.
Who we shouting out?
Maggie.
Shout out Maggie. Shout out Emily. Okay, there we go. What if they did?
I'll tell her to.
Like Maggie, like if you ever go to college and like need to look back on one of these, it'll be there on YouTube, which is kind of nice.
Wow.
I had Emily, you guys know Emily Hammond, she just graduated. She told me the other day that her AP score got her out of her Toledo college. And she's also tutoring sophomores because of her AP Chem knowledge. So, you guys are going to be so well prepared. What's that?
Oh, wait, you mean her credit on...
She got out of her Chem 1, and she's tutoring sophomores. She's tutoring sophomores. So hopefully that'll be you guys.
Did she get like a 5?
I can't tell you what she got on her test.
Probably got 5.
Probably 4.
I can't say, because that would be like confidential. But she got out of it. So,
Wow.
okay. So those are strong acids, but good job, Emily Hammond, if you hear this. All right. Okay, strong acids. Strong acids, this is really important. Strong acids completely dissociate. When you hear the word dissociate, what do you think of?
Leave.
Yourself. Okay. Leave. What else? Break up. Strong acids, when they hit water, they immediately break up into their ions. So when I put hydrochloric acid in water, it immediately breaks up into hydrogen and chlorine. Completely. Completely. That's why they're strong. In fact, when I was mixing up acids this morning, when that happens, when you rip off, let's say I was doing sulfuric acid, when I rip this apart, guess what this SO4 wants to get once the H2Os are gone? More hydrogen, right? So it's literally ripping the hydrogen off of water. It gets super, super hot. It's super exothermic. Super exothermic. So strong acids completely dissociate. That's really important. They are strong because they completely dissociate. They break up. I mean, all acids can be bad. You wouldn't want to like come into direct contact with full strength of these. Hydrofluoric? Hydrofluoric is not one of the 6. The AP Chem wants you to know. Okay. Strong bases. Strong bases. So you just kind of need to know this. These are your alkali metal hydroxides. Your alkali metal hydroxides. So can somebody give me an example of an alkali metal hydroxide? LiOH. Give me another one. NaOH. I don't know why I put a comma in. KOH. Those are all alkali metal hydroxides. Anybody guess what strong bases completely do? Strong bases completely dissociate. Yes. Strong bases completely dissociate. So these, when they hit water, they immediately break up. They immediately break up. The other weird thing that happened today when I was mixing chemicals is actually this was with my sodium hydroxide. We have these 2-liter Erlenmeyer flask, but some of them aren't actually 2 liters. So I poured my 2 liters of water in, and then I couldn't even fit it all. That's why Erlenmeyer flasks aren't good measuring. So they say 2 liters, but they don't even necessarily hold 2 liters. Yeah. I don't know, it's very annoying. So me and Mr. Worth immediately recycled that one and ordered 4 new ones, because why do I want a 2-liter flask that doesn't hold 2 liters?
Wait, why would you want that?
I don't know.
But why would you order the same one?
No, we ordered new ones that will actually. Because there's Pyrex and there's Chemex. This was the Chemex brand.
I'm a big Pyrex.
Yeah, don't get Chemex. She's the worst. No, she's the worst. Okay, don't dissolve easily. Any guesses? If strong acids dissolve easily, weak acids do not dissolve easily. So some weak acids would be, this is everything else, by the way. So if it's not if it's not one of those 6, it's going to be considered a weak acid. So H3PO4. Everybody know what that is? How would you name that? Phosphoric acid. Anybody know where you find that? Let's do one more. What about H2CO3? You find these both in popular drinks. You'll find H3PO4 in Coke. You'll find H2CO3 in Pepsi. How do acids usually taste? Sour. Acids usually taste sour. All right. If you are a young lady in this room, what are you more prone to than the young men in this room?
Dr. Pepper. Wait, what?
Dr. Pepper, for real.
I thought talking about soda. There you go. Yes, W answer.
Pregnancy.
You knew it. Oh, wow. W answer right there. Dr. Pepper.
Oh my gosh. This is going crazy.
I thought you meant.
Here's the problem. I can't even think of what I'm saying right now.
I don't know what you're asking.
When you don't have enough
Anger.
calcium in your bones, osteoporosis, yes. Also true, all right? Osteoporosis, young ladies are more prone to osteoporosis than young men. It's just scientifically proven. If you don't want to get osteoporosis, don't drink these dark pops. Here's why. Guess what? We're going to talk about that in a second, all right? This hydrogen, once it's ripped off, guess what it's looking for? Oxygen, all right, because it wants to form water. Guess where it's going to find oxygen? In your bones, or the calcium, all right? If you break this up, guess what? The PO4 is looking for calcium, and that's going to form calcium phosphate. This CO3 is looking for calcium. It's going to form calcium carbonate. That calcium is getting sucked out of your bones when you drink these pops. I'm just saying, I'm trying to give you, now, Mountain Dew has citric acid, which is actually better than this. It's actually better than this. I can't help, what's that? Starry? I think that's going to be a citric acid, a more fruity acid. The fruity acids are better because those are more natural. Those are more natural acids. Lemonade? Yeah, you're good.
Wait, is there still those if you have like
Diet?
Diet? Is
Yes.
it the same?
There's still those, and then you have the fake sugar, which isn't necessarily a great thing either. And it tastes horrible.
Sugar is so good. It tastes. You guys all
No,
get
diet.
cancer.
Yeah.
What?
Yeah. The other most popular acid, I'm trying to help you guys, I'm just saying, is pregnancy. HC2, I didn't think of that, but yeah, HC2H3O2. Does anybody know what HC2H02 is? That's acetic acid, also known as what?
Acetic acid.
Also known as? Vinegar.
Yeah, W answer, guys.
Vinegar is water and acetic acid. You do not want to just be drinking vinegar, all right? That's not good for your teeth, all right? Vinegar is actually not good for your teeth. What do you use vinegar for in your house? Cleaning, all right? Also fries, all right? Also fair fries. Now, it's not great for your teeth. Now, do I put as much vinegar on my fries so the bottom of the cup falls out? Yes. I do that at the fair. But that's only once a year. And then I put so much salt that I can see it. Then I drizzle it in ketchup. And then I eat it with a fork.
Hey, you never said that salt is bad. You just said that I'm trying to eat it.
You need salt to live. Salt's not bad. Helps you not cramp up. Right. So, acetic acid, vinegar. Okay. For the weak bases, I've got an even better story. All right. Weak bases. I've got two I'm going to talk about. One is NH3, which is ammonia. And the other one is NH4OH, or ammonium hydroxide. Weak bases are usually used as cleaners. Anybody here live on a farm? You do, Ava?
I have a dog.
Okay, so you know what if you have, anyone who, I have a dog, okay. Same thing. I have a cat. I live in the middle of a cornfield. I don't live on a farm though.
I used to have a fish.
Okay, what do farmers fertilize with? Manure or
Chemicals.
ammonium hydroxide. All right? So if you ever get behind a fertilizer truck, you're going to see a major chemical sign, right?
Yeah.
This is a true story I'm about to tell you. In southern Ohio, there was a guy who must have taken AP Chemistry, a farmer. So this farmer it's hilly in southern Ohio, right? He was hauling behind his tractor his NH4OH. He hit some kind of hill wrong, and it tipped. He tipped. So his tractor fell, and this is kind of a gross story, all right? It pinned his leg under the tractor. The NH4OH starts leaking. NH4OH is very, very dense as a gas. He was in a valley. He knew if he stayed there, that NH4OH was just going to suffocate him. All he had was a pocket knife. He sawed his leg through the bone, dragged himself up to the street, and he survived. It's like this, not in Worcester, in southern Ohio. All right? What's that movie where the guy's in the mountains 20-some hours? It was that, but with his leg. So he had to saw through his leg because he knew he was going to die. He knew he was going to die if he didn't do that.
I would take the L.
I'm not taking the L. All right? I'm just saying he survived. I don't know. That dude was crazy. I don't know, but it's a true story. So then he crawled up to the road. Somebody found him, took him to the hospital. Tourniquet, boom, lived. Grady.
Why? Wait, so dig a hole through the dirt and then just like breathe out of there.
No, because the NH4OH is still going to be on top of him. There'd be no oxygen there.
Dig a hole under his leg.
Dig a hole under his leg.
Oh wait, it's on the road. Do that.
Wait, when did he get on? Was it on the road or was he in like?
No, he was in a field. The tractor tire is on top of his.
So why did he dig a hole?
With what?
His hands.
I think that the tire was too heavy. It like compacted the. I'm just telling you what happened. All right? I'm just telling you what happened.
Why are we all like going against each other?
What I'm saying here is if you know chemistry, number one, you won't get osteoporosis. Number two, you may live if you get in a tractor accident. I cannot help you with pregnancy, okay? Cannot help you with that. But Females are more prone to that.
Mr. Heller.
So, yes.
Pop the tire.
Pop the tire,
He has a knife.
but then the rim would have pinned him. It's still heavy.
That's why
I
you
feel like
dig all
if you pop it right, it wouldn't take out.
I don't
Just
know.
like immediately.
This is what he did. We gotta keep moving. We gotta keep moving.
He's got a knife.
Or I guess it either know chemistry or have common sense.
Hey, maybe you pop the tire.
Yes.
You gotta cut the tire and breathe the air in from the tire.
Yeah, why did you cut the tire? No, that's actually so
It
real.
would explode.
He could have really cut
You cannot tell me that.
Here's the problem. Do you know how much rubber you'd have to go through to get to the tube? Also true. Also true. Put the farmer guy.
The guy who saved himself.
All right. HNO3. Legless farmer. That is now Danny's #1 op for today. For today. All right. HNO3. All right. Write this equation. Nitric acid plus water. We've hit it all this period so far. This water, acids are a I can't even talk right now. Acids are a proton donor. So this acid wants to give this proton, also known as a hydrogen, to water. So this makes H3O plus NO3 minus. NO3 minus. Or sometimes if you look at it just by itself, you may see HNO3 just breaking into H plus NO3 minus. This is showing you an acid completely dissociating. Completely dissociating. This is showing you what happens when this completely breaks up. These weak bases, they stick together. That's why when you have a weak base in water, you can drink it. All right, you can drink carbonic acid, phosphoric acid. I guess you could drink vinegar. I don't know why you would, but you could.
Class period, I might do anything along this line.
I don't know.
I might.
All right, flip the page. Flip the page. All right. You don't have to, but you're going to need at least this much space for what I'm about to do. You're probably good.
It's just enough.
I don't know.
I'm gonna be a D1.
Risk it. YOLO. That's what I say. All right. We are now going to talk about YOLO. No. Net ionic equations. Net ionic equations. I feel like that farmer story really got us off topic. All right. So, step one. Step one of a net ionic equation is writing your regular balanced equation. So I'm going to give you an example here. AgNO3, that is aqueous, AQ, that's now important, plus NaCl, salt is also aqueous. It stays in solution. What would that give me? NaNO3. Is that aqueous? Well, shoot, I just wrote it. That's aqueous. All right. Plus AgCl. Get out your blue periodic table, flip it to the back. On the back of your blue periodic table, we're going to talk about a new section that we've never looked at before, even in AP Chem. Look at the square that says solubility rules of salts in water. Solubility rules of salts in water. You will see, number one, most nitrate salts are soluble. Is this a nitrate salt? Yeah. Is it soluble? Yeah. Is this a nitrate salt? Yeah. Is it soluble? Yes. Most salts containing alkali metal ions, LiNiK, CSBr, and the ammonium hydrogen are soluble. Is this a salt containing the sodium ion? Yeah. Soluble. Most chloride bromide iodides are soluble. Exceptions are salts containing silver, lead, or mercury. Does this contain silver, lead, or mercury? Yeah. Therefore, this is not soluble. So, What would I write for my symbol after AgCl? Solid. This is going down if this was in a test tube, because this is my precipitate, my PPT. So the precipitate is the solid that is formed. So you might see PPT, you might see arrow down, you might see solid. You might see solid. So step one in a net ionic equation is writing just your regular balanced equation. Cool? Step two. Step two is your total ionic equation. So write down total ionic. This is where I'm going to break everything up into its ions. I'm going to break everything up into its ions. If something is soluble, it breaks up. Okay? So what's this going to break up into? Ag plus NO3 minus plus. Is this going to break up? It's aqueous, so yes. Na plus Cl minus. Now, what if I would have had, I don't know, CaNO3 2? Then I would have had Ca plus 2 NO3 minus. So if there's a subscript, the 2 goes in front of the ion. The 2 goes in front of the ion. I don't have that for this example, but I just want to talk about that. Okay, that's going to give me, is NaNO3 going to break up into its ions? Yes. So Na plus NO3 minus, because that's aqueous, it breaks up, plus, will my solid break up? No, it will not. So your precipitate always stays together. Okay. The next thing we do is I like to square what we call the spectator ions. Spectator ions are just floating there. They're not actually part of the equation. They're there, but they're not interacting. So spectator ions are things that are on both sides. Do I have NO3 on both sides? NO3 is a spectator ion. What else do I have on both sides? Na. Na is a spectator ion. Those are not going to be part of my final thing. So let's just make a note of spectator ions. Spectator ions, I'm going to put that in a box because we put these in a box. These are ions on both sides of the equation. These are there, but they're just floating in solution. They're not really doing a lot of interacting. Step 3 is to write my net ionic equation. My net ionic equation will tell me what is actually the movers and shakers in this reaction. Well, what do I have left? I have Ag plus, I need to put my plus, Cl minus, and that's going to give me what? AgCl. Does that make sense? Yes. So the ions that actually did something in this equation were silver and chlorine. Is this equation balanced?
Yes.
Is it balanced with charge? What's the charge on this side? What's the charge on this side? What is the charge on this side? 0. What is the charge on this side? 1 positive, 1 negative. 0. So it's balanced in coefficients. It's also going to be balanced in charge. I guarantee you, you will do one of these on the AP Chem test every year. There's always some sort of net ionic equation. Shall we try another one? Okay, let's do a weak acid example. So here's one with a weak acid. So let's look at, I don't know, vinegar. So HC2H3O2, is that aqueous? Get used to looking at your sheet. So look at your solubility rules. Would that be soluble? This is a weak acid, right? It is still, why? What? Does this talk about acetates? This is still It's still a liquid though, right? You would agree that vinegar is a liquid? Yes? It's soluble. It's AQ. It's AQ. Plus, we're going to mix that with sodium hydroxide. Is sodium hydroxide soluble?
Yes.
Yeah, multiple reasons why. First of all, well, it's an alkali metal hydroxide, right? It says right here, salts containing alkali metals, also hydroxides. What's that going to make me? NaC2H3O2. That's a alkali, so that is aqueous, plus H2O. What is my symbol going to be for H2O? Liquid. H2O is a liquid. And then liquids stick together because it's a liquid. Okay, let's talk about these things breaking up. So let's go to my total. For my total, is this going to break up? No. Why not? Why is this not going to break up? It's a weak acids. What do weak acids not do? Dissociate. That's why you have to know the difference between a weak acid and a strong acid. So this is not going to break up. Even though it's aqueous, it doesn't break up. It does not break up. It dissolves, but it's not going to break up into its ions. How do I know? Because it's...
Yeah, which one is it? Which rule?
What are we talking about? This one?
Yeah.
This one, you would just be given aqua. There's not a rule for that on the back. You're usually going to be given your states to start.
And how do you know that if it's a weak acid or a strong acid?
You're going to memorize the strong acids.
Okay.
Everything else is a weak acid.
Okay.
Everything else is weak. So I brought no clean clothes, not one of those. Boom, weak acid.
Okay.
Weak acid. So that's going to stick together. HC2H3O2, because that is a weak acid, plus Na plus OH minus yields. Is this going to break up?
No.
Why not? That's not an acid anymore. This is now a salt. Agreed? Do I not have a positive and a negative? That's going to break up into Na plus C2H3O2 minus plus H2O. So don't get acids and salts confused. Acids start with H, salts don't. That's a salt because I got a positive and a negative. Do I have any spectator ions? Na. Anything else? No. So we can now write our net ionic. So my net ionic is going to be HC2H3O2 AQ plus, we don't have to write the states. You guys, the states aren't super important in the net ionic. AP Chem does not grade if you write the states. You really need them up here to help you figure out what's breaking up, but I'm not going to be grading for states in the net. Okay, plus OH minus, very bad handwriting, gives me C2H3O2 minus plus H2O. Check yourself. Does this make sense? Are these the movers and shakers? Well, what is my acetic acid doing with a proton or a hydrogen? Donating it to what? OH, making what? Water, and the ion remaining. Is this balanced?
Yes.
Are my charges balanced?
Yes.
What's the charge on the left? -1. What's my charge on the right? -1. So they don't have to balance out at 0. They could be both -1. They could be both +2. The charges just have to balance.
What do you do if they're not?
If they're not, then you probably need to add a coefficient somewhere to balance it. If they're not balanced, yeah, so if you get down here and you notice it's not balanced, you probably need to add like a 2 here to balance the whole thing, and then it will balance. If they don't balance, you made a mistake. You made a mistake. Yes. If you do it correctly, the net ionic always will balance.
Without adding any.
You may need to.
Oh, okay. But it always.
So if you end up with like, I don't know, an example would be like, I can't think of one off the top of my head. You'll know. You'll know. Okay, let's do a strong acid. So this is a strong acid example.
Is that a strong?
This was just like a salt and a salt.
Okay.
So strong acid, let's do HCl. You guys did this one on your own, which is AQ, plus NaOH, which is AQ, gives me NaCl, AQ, plus water. So you guys write out your net ionic equation. You may be surprised what your net ionic equation ends up being. First question you have to ask yourself, does HCl break up? Haley says yes. Why? Because it completely dissociates. HCl breaks up because that is a strong acid. So the key of knowing the difference between a strong acid and a weak acid is knowing if it dissociates or not. Oh, that L Camp is calling my name. Cannot wait. I got a can of Mountain Dew with it. Oh,
That's got a hit.
it's gonna hit. I'm gonna eat, no crumbs. Do you say so ionic? I got it.
Yes.
We get it?
Yeah.
Spectators? My only spectators what? Oh, I have Na and Cl.
I was about to say.
I have two spectators.
Only.
So, what are the movers and shakers in this equation? Anytime you have acid-base, you would agree that this is an acid-base reaction. Yes? You always create a salt and what else? Water. What do ionic solids do? They dissolve.
Wait, so a strong acid?
Strong acid, strong base. Really, anytime you add an acid base, you're going to make a salt and water. So I have H plus OH minus, and that creates water. That is the net ionic equation for a strong acid, strong base. So what's actually interacting? H plus, OH minus.
So that always makes it
Every time. You're going to have multiple of these in the lab next week. Multiple of these. Okay. So how do we calculate solutions? What do we use in stoichiometry with solutions? How do we tell the strength of a solution? Not pH, molarity. Yes. We're going to be using molarity. And what is molarity? The symbol for molarity is capital M. And that is equal to what? Number of moles of what? Solute over liters of what? Solution. Of the solution. Or most people just say moles per liter. So molarity is going to become one of our big new conversions to use in stoic, right? Do you see how I could use this to go from moles of something to liters of something? I'm going to flip the page when you guys are ready. We got 5 minutes left. I think we can finish this. Can I flip? Okay. This is going to combine everything we've done so far this year.
How much more room do we need?
I mean, this is going to take like at least half a page for me.
Okay.
So if you want it to stay on the page, you guys decide. Or just YOLO. Did you fit it? Did you fit what you needed to? Okay, good.
All three problems in there.
You write so much smaller than I do. Okay, so let's say I start out with 24.3 milliliters of 0.200 molar lead to nitrate reacts, when you think of the word reacts, what are we thinking of in our equation? Plus, right? Plus, reacts with 36.7 milliliters of 0.250 molar sodium iodide. 0.250, 36.7, 36.7 milliliters of 0.250 molar sodium iodide. I would then ask you, how many grams of lead to iodide is formed? What all have I just asked you to do? I've asked you to do several things. I've asked you to write a balanced equation. Kel, what else did I ask you to do? Determine the limiting reactant and then solve for the theoretical yield. I've asked you to do all of those things with this problem. Let's write our balanced equation first. So I have lead 2 nitrate, which is going to be PbNO3 parentheses 2. Agreed? That's AQ, just for funsies. Plus sodium iodide, NaI. That is also AQ. You can look at your solubility rules to see why. That's going to make how many grams of lead 2 iodide is formed? Well, if I can get grams, that means lead 2 iodide must be my what? Solid, right? PbI2, that's going to be my solid. That's going to be my precipitate. Plus, and check that out on the back. On the back, I have chloride, bromide, iodide, salts are soluble. Notable exceptions are lead 2. So that is on your solubility rules. Plus, my other one's going to be NaNO3, which is super soluble. Is it balanced? No. I have 2 NO3s here, so what do I have to put in front of this compound? 2. That gives me 2 NAs, so what do I have to put here? 2. That is now balanced. And I was told that I started out with 24.3 milliliters of 0.200 molar of this, and I have 36.7 milliliters of 0.250 molar of that. I want to know how many grams of precipitate are formed. So I like to write down what I've got. Write down what I've got. So first step is run both of these to what? Moles. Okay, so let's do it. So let's start out with our PbNO3 So I'm going to start out with my 24.3 milliliters of PbNO3 Can I use milliliters for molarity? So I'm going to say that there's 1,000 milliliters of PbNO3 in 1 liter of PbNO3 and I know for every 1 liter of PbNO3 how many moles do I have? 0.2 moles. 0.200 moles. Do you see how you use molarity in your stoic? Have you guys done? Did you guys do this last year?
I think we did not do that. Rob did not.
I definitely saw the capital N, but
Okay. Well, that's what you do with it. It's moles per liter. So let's get our moles of this.
Oh, that's good.
Yes. The big M is turning into moles per liter. Yes.
like about the AP exam, do they look at your work and like notice if you label all of it, or is it just like whatever your answer is?
On AP Chem, you must show enough work that me as a grader, I as a grader can tell what you're doing. You're not going to get graded on having these. I want you to show it though. Eventually, it just really helps you keep track of what you're doing. So if you had this 24.3, 1001, 1 liter 0.20, me as a grader, I'm one of the 300 people, I know what that means. Right? I'm a chemistry teacher. I would know what that means. I just think it really helps to show it. Okay, what'd you get for your moles? .00 486 moles of PbNO3 parentheses 2. Yes? I don't care if you show me the work for milliliters. On the next one, I'm just going to do this in my head. How many liters is this?
0.00367.
Would it be 0.0367? Move it 3? So 0.0367 liters of NaI. It just saves a step. If you want to show it, it makes you feel better, do it. Because if I do like this, then I'm straight to, for every 1 liter of NaI, how many moles of NaI do I have? 0.250 moles. 0.250 moles of NaI. Boom. I'm already at moles. So solution stoic, you're kind of saving some time because you don't have to go to the mass. What'd you get?
0.00918.
8 moles of NaI. And I know for every 1 mole of PbNO32, I need double of the other one. Yes? So for every 1 mole of this, I need 2 times this. 0.00486 times 2 is what?
0.00972. 0.009.
That's bigger than this, right?
Yeah.
So therefore, this is my what? Limiting reactant. Limiting reactant. Then I'm going to take my limiting reactant and do what with it? Run it to grams, the other thing. You got it. So 0.00918 moles of NaI times, stoic step, there are 2 moles of NaI for every, what are we solving for? PbI2? For every 1 mole of PbI2, every 1 mole of PbI2 is 461.008 grams of PbI2. That will give you your grams of PbI2, which should be 2.12 grams of PbI2. So it's just one more step in our thing. Wait, not yet. I got one more thing I want to write down. When we're diluting solutions, this will take less than 30 seconds. When we're diluting solutions, you're going to see this equation, molarity 1 times volume 1 equals molarity 2 times volume 2. M1V1 equals M2V2. So I could give you 0.250 molar of 1 liter of something, and then I could say, I want to make that 0.5 molar. You just solve. Nice work today. Nice work today. So this is just a plug and chug. You'll get 3 out of the 4. It's super easy. Tomorrow, lab prep day. You should not need goggles tomorrow.
Are we starting lab lunches tomorrow?
Wait, I thought
We probably should lab lunch
I
tomorrow.
thought we had more notes tomorrow. Yeah.
Oh, no, not tomorrow. You're right. Tomorrow I have notes. No lab lunch tomorrow.
I was gonna say.
Because tomorrow people are going to the science club table.
Right.
Okay. Tomorrow, regular day.